Well, I think we can get started. Welcome back, everyone. So we have a definitely unusual situation in this classroom. If you're curious what happened, they decided to upgrade our projector over the holiday, which is not a bad idea. It looks like it's a nice projector, about like 3 times as big as that one. So it's going to do a good job for us. But they didn't test it out and it's absolutely not working. They're in the classroom right now, breaking things down, probably trying to refish cables and all that sort of fun stuff. We'll possibly be back in that room on Thursday, but I'll definitely let everyone know before that class starts, so we'll know which room we're in. Also, before I get too far ahead, they don't have very many rooms with L cameras anymore. This classroom doesn't have one, so we're just doing the best we can. And for Ana Benitez on Zoom right now, are you able to hear me okay if the microphone is about here, or should I put the headset on to come through clearer?
You sound pretty clear.
I think I should put my headset on. I'll just go like that. How about now? Is it coming through a little bit better, Anna?
Yes, that sounds good.
Awesome. And I have a second problem. These are noise cancellation headphones, so I can't just tune out the class. I'll do something like this. I'll just look like a dork. No one's recording it, I hope. Okay, so any questions, folks, before we get started? Okay, well, so far, with where we're at, there's no quiz that's due today. We didn't assign one over the break. That just seemed like a rude thing to do. So instead, we'll have one last quiz. I'll have it posted on Wednesday before we come to our Thursday's class. And these are the last 3 sections we're working through. I'm not going to try to complete all of them on this week. We're going to take our time, work on these slowly and carefully like we've been doing with all the other sections. And my goal is to have 6.7 completed probably on Tuesday of next week. That way we should have all of Thursday of next week to review for the upcoming final exam. So that's where we're at so far. And really, it's not too much of a list of problems to get through. Here, we're just looking at all the properties of logarithms. We'll use them to solve equations here. And then we'll take another look at modeling, looking at, say, exponential growth, exponential decay, whether it's money and investing or something else going on there. We'll look at, again, at these kinds of application problems that we saw before. But now that we have equation solving capabilities, we can ask slightly larger questions about those problems. So that's where we're at so far. And for the further announcements, we have an extra credit opportunity that's on the table for us. It's nothing huge or major, but here's pretty much how it works. There's an opportunity to always evaluate the course, whatever course you're in at ISU. So if this is your first semester, you probably are learning about this for the first time. If it's not, then you're probably heard about this stuff a lot, and we'll just get it out of the way. So the way course evaluation works is if you go to the very top of the Moodle website and pop out this little bar here, then there's a whole bunch of other stuff. I don't usually use too much here, but this is where the course evaluation actually is. If you click on this thing, you don't have to do it right now. You can do it, say, after class, but it tells you about its purpose, why we want to do it, and click on this right here, and it'll just take you to a really short survey. It's fully anonymous. It goes to the department chair. And so it's your opportunity to say what you liked about the class, what you hated about the class, whether it was the course materials, ALEKS, the exams, anything you'd like to talk about. You'll have the opportunity to express your emotions and things like that through the survey. Once it's done, there'll be a completion page that just says, thank you for completing this survey. If you take a screenshot or just an ordinary cell phone picture of your screen, that's fine as well. Send it to my ISU email address, and that completes this extra credit opportunity right down here. So send that to me, that completion screen. And if you miss the screen, it's okay too, because you can go right back to the course evaluation and it'll say, you've already completed the evaluation. You can send me a screenshot of that as well, and that works just fine. So what I'll do then for the extra credit is I'll drop an additional quiz grade. That's not super exciting since some people are doing really quite well in their quizzes. We're already dropping 3, so if I drop an additional, that's dropping 4, which might not change people's scores at all. And so the next best thing I can do is, if dropping a quiz won't change your grade at all, maybe your quizzes are all 10s or something like that, I'll go to your ALEKS assignments and I'll drop your lowest ALEKS assignment as a next best thing. I can't do any further extra credit. The math department forbids extra credits with exams and such. But that's what you could get for extra credit out of doing that activity. Any questions about that so far? Okay. Aside from that, if we keep on scrolling through here, This is another extra credit opportunity that we mentioned before. I think it was after exam 1. Your final exam score can replace your lowest exam score amongst exams 1, 2, and 3. So that's just pretty much a reminder. It's been there for a while. And continue to scroll down. In our finals week, we're only meeting on Monday once just to complete the final exam. It's going to be held from 3 to 5 p.m. in the classroom 215. That 215 is settled. So whatever's happening with the technology, it won't matter. We don't need a projector for that final exam. The math department also requires that it be taken on Monday. They have one common exam that they give everyone in the entire university on that one day. And other things I should mention is I've been continually getting confused with what the math department wanted for a so-called note card on the final exam. And I've made a screw up on there. It turns out it is completely closed notes. There is no note cards that's available on the final exam. Sorry about that, folks. What they are including is this right here, the formula sheet. It's not a bad deal. This is going to be on the real final exam. It'll be like the last page. You can just tear it off so you can have it available for you. It'll have lots of great stuff like properties of logarithms that we're about to get into really quickly. Other interesting things like these technical theorems, they're all just posted here. So if you don't have them memorized verbatim, that's okay on this exam. And the good news is there's 2 pages at least, so I kind of like that. Here's more things about polynomials, exponential functions. This stuff right here is pretty helpful because it's also your compound interest formula. So if you didn't have that memorized perfectly, that's okay on a final exam, as well as the other 3 models that we've been taking a look at. And then information on transformations. So they gave us 2 pages there, and that's going to be the deal for the final. That way, what I would do to study for this final is I would probably print this off early, in fact, even though it's provided on the final. That way, when you go to study, use this as well. Familiarize yourself with this sheet so that you can know where things are, how to use the formulas. It'll also enforce in your mind what's not on there, the stuff that you really do have to memorize when you come to the final exam. Stuff like, for example, quadratic formula and other stuff like that. Well, that's my spiel so far about the final exam. Any questions at the moment, folks? Okay, so that was my screw up there. Sorry, that looks like not teaching this class for some years. I've been a bit out of the loop. It's closed note card, but this sheet will be provided. And there's another screw up on the final exam. We didn't catch this before it went to print. The math department put instructor here, should say student. That's a really weird typo. So I'll just remind people when I give the final exam, make sure you put your name right here. I know you're not the instructor of the course, but that's okay. We'll just live with that and they'll be completely fine. So this is the real first page of the final exam. They've already been printed at this point. And it just has some basic information of how to answer questions. Interval notation is hugely emphasized, so it's being asked to always state your intervals with that. Asymptotes have to be equations, and exact answers unless instructions say to approximate are kind of the standing rules. Then all this is more for the grading purposes. I'll just be tallying up points and putting down a total and a percentage once the grading's complete. So that's the real first page. This is the real last page with the formula sheet. And again, probably a good idea to print this out early and use it as you're studying for the final. Any other questions so far, folks, with all these, what's about 8 minutes of announcements so far? Okay, well, let's take a look here. If we continue to scroll, here's a couple ways you could start to study for the final exam. I don't think I have anything up here, but if you go below the final exam information, this is a document that I wrote many years ago, well, a number of years ago, not that long ago, but it was out of a different book. So if you open this, it's kind of confusing what the sections are saying. This is absolutely not our book, but these problems are still interesting. They're still pretty educative, I'd say. If you'd like, you can go through this document, and it has at the very end, full solutions are provided on the very, very end of that document. I didn't provide actual problems from our actual textbook because I felt like that hasn't been a really huge resource for folks. I think a lot of people are using other resources to study. So this will be our sample final. And these are the exciting ones. These are real final exams that were given in the past when I taught the course. I don't have full solutions for all of these just yet. I think some of the older ones, if you open them, you'll see solutions at the very, very back. Maybe not. Some of them I think do, maybe not all of them though. But I do intend to upload all of the solutions to every one of these exams before we meet on Thursday's class. So if you want to give them a try right now, you can print off any random final exam and just give it a shot. Then once the solutions are posted, you can check your work, see how you did on those problems. So I think that's my full spiel of announcements. Any questions at all, folks, about the exams, upcoming sections, or anything at the moment? Okay, well, let's give this a try then. We're back to section 6.5. And here's pretty much where we left off. We completed example 2 where we were just evaluating expressions. And a lot of the ways that we got these evaluations was just properties of logarithms. Right here in part A, I think this is a good point to just do a warm-up and look at what really happened right here. We're using the formulas in this box that says b to a power of the log to the same base b causes a cancellation and you just get x. And also log base b of b to the power of x is also a cancellation, giving x. And that's just because we have a set of inverse functions. So over here, we hit that cancellation and we just got a 5 out. Let's start off by expanding on that formula in the orange box here. And write out a new set of formulas. It's really the same exact stuff, but what's tricky about math is definitely the notation. If you see it as this property, then that's just the way to say it generally. But for you using property 1 in part A, you might be visualizing it slightly different. It would look like this: e to the power of the natural logarithm of x is x. That's what we used on part A. There's an immediate cancellation, e to natural log x. So if you change b to e, and e right there, the log base b just turns into ln. Does that make sense to folks so far on that one? Okay, so then property 2, in case it comes up, probably most certainly will in these notes, would look like this. The natural log of e to the x is just x. So same exact formulas, but these ones are now just talking about base e. And they certainly look a little bit different. Our goal is just to train our eyes to see this box formulas as the same exact statement of up here, those boxed formulas. Any questions so far? Okay, so it's great to have all these formulas, but here's the bad thing about them. We also have to know where the formulas break down, what we can't do. And so here's our next warm-up question to start today. Let's suppose we were to evaluate, let's call this maybe part E, just throw in a new one. And it's going to be e to the power of 2 natural log 3. Now suddenly part E is a really, really tricky problem. There is no cancellation on this one, and it doesn't even seem fair. We have the right base E, and natural log is also a base E, but there's something preventing a cancellation just immediately at this step. Anyone spot the trouble? Exactly, this 2 right here means there's a no-go on this property in the box. It really has to look exactly like this: base E and the natural log with nothing right here. Then anything inside, whether you call it x or not, just produces an x out here. So our first job on this problem is take care of that 2. It turns out that 2 becomes an exponent. It squares the 3, so this is natural log of 3 squared. Now a cancellation right at this step will happen. Those completely just annihilate each other. You're left with 3 squared, which comes out as a 9. So this problem is definitely tricky. There's lots going on when you see these kind of properties. And if you don't have a 1 right here, the whole property doesn't work at all. Imagine what we would have got if we did cancel at this step, even though it's wrong. That might leave it a 2 and a 3. We might have said our answer is 6, which is definitely not quite right at all. And so that's the purpose of being extra careful whenever we see new formulas like these kinds of things. Well, I would consider these still kind of just warm-up questions. Any questions or comments at the moment? Okay, now let's scroll down to some of the newer material. We left class going for our long break, pretty much just eyeballing this table. We didn't do too much with it except do our part A problem right over here. So let's take another look at how this went down, and we'll try it out again. So the gist with logarithms is we're really just working with exponents in a different kind of way. And every exponent law has a corresponding logarithm property. So if you have b to the power of x plus y, you're multiplying b to the power of x times b to the power of y. And likewise, if x and y are multiplying, we can just expand out and write log base b of x plus log base b of y in this kind of way. If we're dividing, there's a minus on the exponents and a minus with logarithms. And this is the property that we used on part E. If we're taking b to the x to a power p, exponents multiply, you just get x times p in this way. And likewise, if you have log base b of x to the power of p, p moves down and you can take p times log base b of x. That's what was happening right here with this 2. We did it in the opposite way. We want 2 to be eliminated from that spot because we want to cancel right here. So the exponent 2 moved up to this position, is where it landed. And that's just this property right here. But it's going backwards. It's going in this direction. Does that make sense to folks so far with that property? Okay, well, our goal is to practice these even further, so let's give some more a try. And probably what I'll do is, as we do these problems, these are brand new properties, so let's maybe carry this table down as we go to solve. So this is the major meat of the new properties right here. And the instructions say use properties of logarithms to evaluate each expression. Evaluation means we're just trying to get a numerical answer, like the -1 we did on this problem. To start off on this, we have the same kind of problem as before. We cannot do anything with properties of logarithms, like say this property here, unless we take out the coefficient of 2. There's no coefficients here, so we have to match that expression. So the first thing that happens is coefficient of 2 will become an exponent on e power 4. So we're using this property right here. So the way we can write out the step is, right, equals natural log. I'm going to put an extra parenthesis with e power 4. And the power 2 goes right here. Then it'll be plus natural log e power -11. So now that we're in this stage, we're in much, much better shape. And honestly, probably I didn't even need to copy that, right? That's just a -11 in a weird format. So we have inverse functions like before, those cancel. And at the same time, well, I could do a cancellation here, but let me simplify it a bit first so it's just more readable how the cancellation works. We're going to get natural log e to the power of 8. So what happens with these exponents is they will just multiply together. This is really e4 times e4, giving us e power 8. Then we'll have a cancellation here on the next step. Let's carry in this cancellation. This just results in a -11, copying in. All we have to do is cancel once more. Natural log and base c can now cleanly cancel in this format. If we canceled over here, it might not be clear that we're getting an 8 out. So it's good to simplify first before we start using too many properties. So next step. Here we're just carrying down the 8 that survives. Then it's 8 minus 11. And our whole value is -3. Kind of a tough problem doing it by hand in this way, but it's certainly really good practice. We're going to have to do these kinds of things for equation solving, and even in these notes coming down, where there's no numbers at all. But if you do see this kind of problem in ALEKS, honestly, there's no harm in taking this and just double checking your work. If it's an ALEKS problem, then that's a great opportunity to take that extra thing. So let's do it ourselves. So I'll use this calculator like before, just because it's really quick and easy to show in class. And let's put in just that whole expression. It would go 2 natural log e power 4 plus natural log e power -11. And that's our double check. We're really getting -3, so we're on the right track. Well, does that look right to folks so far? On paper here or trying it out in the calculator? Awesome. Well, let's try this out again then for our part C down below. And for these problems so far, I'm going to highlight in yellow anything that I feel like is just exceptionally tricky about the problem, where it's easy to go through, but if we missed that one little thing, our answer might be just totally incorrect because of something small. So I'll try to keep highlighting in yellow those weird little things that cause tiny amounts of trouble. Now let's give part C a try next. So it's log base 6 of 4 plus 2 log base 6 of 3. And these problems are truly kind of tough because I cannot calculate that exactly. Even if I tried to do it by hand, I'm going to get just some abstract expression that I would have to put in a calculator. Same with this right here. I have no idea what 2 log base 6 of 3 of is. But if we combined all this stuff together, it suddenly becomes really clear what the answer should be. So let's give it a try. First thing to start off is that 2 right there is what's causing the trouble. So we'll use logarithmic property right down here, property 3, and say that this is log base 6 of 4 plus log base 6 of 3 to the power of 2. Or you could just say log base 6 of 9 at that step if you prefer. Now finally, with that done, we have addition right here, which says we ought to use that first property. This now is turning into log base 6 of 4 times this quantity, 3 squared. I'll just write this in as a 9. Then multiply inside. Now we're just following order of operations, and we get log base 6 of 36. At this stage, if you did put it in the calculator, no harm done. I don't think that's a terrible thing to do, but it is a good idea in math to always kind of look before you leap. Any volunteers for what this answer should be, just by eyeballing it? It's 2 exactly. Good call. Here's the thought on why it should be 2. Whatever this comes out as, this is the exponent that we have to pick out the base. Our base is 6. So we'll say the exponent, that 6, must be raised to obtain the actual input. The input was 36. And so you're absolutely correct. That exponent has got to be a 2. Because if you put a power 2 on this 6, you're squaring 6, resulting in 36. And that's the correct value of that logarithm right there. So this in orange is just kind of a review of what logarithm is trying to give us. It's always giving us an exponent. And that's why we have these properties of logarithms. But there's another way you could check this out. Logarithms are weird in that there's lots of different ways to think about them. If you're not sure on this too, you could take what's effectively a logarithmic equation, this portion right here, just convert it into its exponential form. In exponential form, you'll have a base 6 down here. Set that equal to. We take the output, which is 2, throw it over here. Take the input, which was 36. It's now an output, so it goes towards the right. And if you believe that equation's true, the equation on the top must be true. Yep, 6 squared is 36. So that's a different way to double check that that is the right evaluation. Let me put a box on this answer since I kind of have stuff everywhere here. But again, think of parts A, B, and C. Still kind of just warm up. We're getting used to the properties of logarithms. And as we go further, we're going to use these even more. But the problems are going to start having things like X's, Y's, and Z's, and so on. And so we won't even be able to put all this stuff in the calculator. We'll be forced to use properties of logarithms to do the next 2 kinds of tasks. So just 2 more topics. We want to see how to expand logarithms and contract them as much as possible. Any questions or comments first before we take a look at the new content? Okay, I did put some additional notes with this. And like I mentioned before, when you start to throw down properties like these, they're really, really dangerous because there's a lot of things that are not properties, which sometimes we feel like they should be. So here is finally the full set of all the properties of logarithms, 1 through 7. These are the common ones. There's also the change of base formula somewhere in there that we don't use quite as often. But I consider 1 through 7 here as the main list of properties of logarithms. So this is a good one-stop shop for working on these things. But notice what's missing in this list. There's no property where you have log base b of x plus y whatsoever. It's just gone. That's because that property doesn't exist. There's no property of log base b of x minus y or anything of that nature. And that's the warning or caution down here below. In algebra, addition and subtraction sometimes seem nice, but they cause a lot of issues. Lots of things that we think addition and subtraction should work with do not work at all. For example, the square root of a plus b is not the root of a plus the root of b, unfortunately. Here's a really fast example. If you took the root of 4 plus the root of 16, it's really order of operations. You must add to get root 20 and simplify to 2 root 5 if you like. But if you split them up, well, the root of 4 is 2, the root of 16 is 4, you would have gotten a 6, which is absolutely not correct. The answer is really 2 root 5. Same issue here with divisions. If you cancel across addition or subtraction, we have another massive problem. These are never equal unless by chance. And here's the other problems. With natural logarithms, if you see a plus b, a minus b, unfortunately, that gives us nothing. There's no property for that. And here's our example. Natural log of e plus e. You wanted to follow order of operations like we did up here. So that's natural log of 2 times e. Well, you could split that up. Here's a property here that says natural log 2 times natural log e. That's the same as natural log 2 plus natural log e. We can split them up. Here, natural log e, that simplifies. And we get just a 1 from natural log e here. So if we try to split them up and write natural log e plus natural log e, it is an incorrect step. We'd have gotten 2 instead, which is very different than natural log 2 plus a 1 right there. So that's the warning on this kind of problem. These are wonderful properties to have, but there's a lot of stuff that doesn't work. And this kind of mistake right here is extremely common, especially on, say, an exam setting. So avoid this kind of stuff, and you'll be in really great shape of logarithms. So here's our properties above. And like we mentioned right before the break, that was a long time ago, there's really 2 kinds of things we would want to do with these properties, and they have specific reasons. In example 4, our goal is to use properties to expand each expression. Yo is not the right choice here. I was trying to reserve that for trickiness. So this is weird because this is not something we really take advantage of a whole lot in this class. But if you're going on to calculus type topics, this is something that comes back in really very full force. If we're a little bit rusty on logarithms, then calculus can just be really, really vicious in certain sections. So we use this for differentiation or integration. We try to expand things as much as possible to make them simpler. Then in example 5, this is very relevant to us. Sometimes we take things that are expanded, like this right here, and we want to compress them down into one logarithm with a coefficient of 1. And this is more for equation solving. So this is something we will take advantage of, and we'll use these ideas in the further sections. But think of it for the section purpose of these notes. Example 5 and example 4 is the same problem. We're just going in a different direction. So you're really doing the same thing, whichever way you take a look at it. So let's start off at example 4. Any questions first, folks? Okay, so here's our properties of logarithms, and our goal is expand this expression. If you're pretty good at this, I might be going kind of slow, but the goal is really just to see how we're using each one of these properties and how to actually execute those properties. First thing to notice inside here is we have an x times a y. So that strongly suggests try this property out. We can take the multiplication between x and y power 7 and put an addition between them. So it just says log, but that's implying this is log base 10. Let's just put that as a statement here. Log x y power 7 is log base 10 of x y power 7. But I'll just use the shorthand. This is just a reminder of which logarithm we're actually using. So first step on this one is going to be log base x plus log base y to the power of 7. So this plus here came from property number 5. Any questions, folks, with that first step? Okay, I would say this is most of the work, but it's still not considered fully expanded. We have to mess with that 7 right there. And so that 7, we'll use property number 7 to just change its location. Here it's in as an exponent. We can turn that into a coefficient. We now have log of x plus 7 log of y. Then at that stage, this is where the problem ends. There's nothing further to do with it. And so we just leave it in that format. Does that make sense to folks on how we expanded this out? Okay, let me put just a little dot here. Actually, that makes it kind of unreadable, but we took the multiplication to make it addition. Then we took exponentiation and turned it into multiplication. Well, that was so fun. Let's try it out all over again. Let me just take another screenshot of this. I want to try to keep the color coding consistent on how we're using those properties throughout. And so let's try this out again on this problem here. Now, part A, part B, they really go together. They look like the same problem, right? But there is a small subtle difference. Here, the power 7 was only affecting the base of y. Here, the power 7 is affecting both x and y as a base. So I put these problems together because seeing the difference between them can really cause a lot of frustration to be eliminated in ALEKS. Also, this could potentially be a tricky problem in a real exam. So wherever the 7 is truly does matter. On this problem, the first thing we have to do is move that 7. We can't break this up until we do that first step. So this becomes first 7 times log of xy. So here, if the entirety of everything inside is being affected by the exponent, that has to be our number one step. Eliminate that exponent. Now we can use the multiplication between x and y right here. Let me see if I can fit that in. You don't have to put in the multiplication dot, mostly just for emphasis. But now we can split this up. This is still a really dangerous problem. And when I write down the result, there's going to be a mistake right here. Let me know if you can spot it and what the remedy will be. I'll put in 7. Then we know there's a multiplication, so we're going down to property number 5 and splitting this up with an addition. So this is going to be log of x plus log of y. But this is definitely not right. This is wrong. Anyone see what's wrong about it? Exactly. So there's 2 fixes here. Either just write in a 7 here, or you could put in a parenthesis. Let's go with both routes. I think when they say expand your expression as much as possible, they really mean expand everything. So we're going to put a 7 in both, like you suggested there. So that's the trickiness of this one. If you use a property that causes addition to show up, like we just did here, and if there's something already multiplying, we can't get around that. It has to be multiplying as our first step. It means you have to distribute on this step right here. Again, all this is not necessarily the worst kind of stuff, but it's very tricky. We have to train our eyes to see this step so we're ready for it when this kind of stuff comes up. So watch out for a coefficient and a multiplication inside those logarithms. This becomes, as our end answer, 7 log base x plus 7 log y. Sorry, I said that weird. That's log base 10 of x. So just log x. Well, that's our fix on this one. Any questions, folks, on getting through that part B? Okay. Well, our goal today is to practice a whole bunch more. So let's see what else we're getting into. So this one doesn't have any nasty trick like that 7 that started off the whole problem. Here, we notice that there's just a division to start us out. So we're going to use property 6. Just need to come up with a color for that. Let's go with purple for this one. The way property 6 works is, if you notice a division, then you just get a subtraction right here. Contrast to if you notice a multiplication, you have an addition right here at that stage. So the way this problem will start off is, we notice it's e squared divided by 5 power x, and write in natural log e squared, and then minus natural log of 5x. So that's our first step there. And now property number 6 is done. There's nothing further we have to do with that. Does that make sense to folks so far? Okay, next, I wouldn't do a whole lot with this one. In fact, I wouldn't even use property number 7, even though there is an exponent here. This whole quantity we can calculate exactly. Any volunteers for what the value should be of this circled portion? It's exactly 2, good call. And the way it's exactly 2, let's highlight the property on this one. It is because of property, let's see, it's natural log first. So it's this property right here. The x that we see here is playing the role of 2. So this whole thing, here's how I usually visualize it. I cancel that way, and it just leaves a 2. So this is going to turn into 2. Now we have to expand this stuff out, so we need to be really careful. This is 5 times x right here. And so now we're using property number 5. But there's a coefficient in front of it, so we also need parentheses, like in that prior problem. Let's start by writing down our negative sign, just copied in, our parenthesis, and then let's expand natural log 5 times natural log x. That'll turn into natural log 5. The multiplication in blue becomes an addition sign. And then from here, natural log x. So we've gone through all of our properties so far on this one. All we have left to do is just expand that negative sign, and the whole problem is done. So this turns into 2 minus natural log 5, then minus natural log x. Let me fix those parentheses inside there. Okay, so that's where the problem finally ends. This is its most expanded form possible. We have a constant minus another constant minus an actual function involving x. This is the only part that actually varies. But any questions, folks, on solving this one? Okay, let me change ears. I can feel myself. Feels like you're going partially deaf if you put in noise cancellation headphones on just one ear. That's an odd sensation. Let me fix that there. And let me recopy this with a new highlighting. Oh dear. Sorry, I'm struggling with the keyboard for just a moment. I think I got it. And now let's try how to one more, or several more. Okay, so at this stage, they're definitely looking nasty. But honestly, if you see stuff like this on your ALEKS homework, it does come up in ALEKS. It's not as bad as it looks. We just have to break this down slowly. There is a new element on this one, though. Right here, we have a 5th root of xy to the power 4. So let's write down a formula that's going to handle this scenario whenever it comes up. We've used this idea before, but now it's definitely a vital idea. If you see, say, an nth root of a for anything, any algebraic expression, whether it's a number or something that involves a variable, to say power m, this turns into a to the power of m divided by n. So the nth root becomes a divisor on that exponent. And if there's no power on a, it would just be a 1 divided by n. So here, if we have a 5th root, that means we're going to have an exponent of 1/5 that's popping out. And that ought to be a really first step on this one. So let's turn this into log base 7 of first, where we had a 5th root, let's put in power 1/5, and it's going to be x times y power 4. Then z squared down below, and that's how our problem starts off on this one. So this problem is a little bit trickier because of all the extra stuff, but it's really definitely not too bad. Here's how I'd probably start off this one. The first thing you want to do is actually use property number 6. Property number 5 doesn't work because 1/5 is not involving z squared down below. So 1/5 has to stay right here until we get to the next step. So here's where we're looking at first. Because there's a division here, we can say that this is equal to log base 7 of, first the numerator goes in, and it's x y power 4 to the power of 1/5. And that extra parenthesis right here encapsulating both x and y power 4 is definitely needed on this thing. Then it'll go minus log base 7 of z squared. So that is done. We're done now with property number 6. All we have to do is expand this stuff and move that power 2 down to get to the last portion. Any questions at all, folks, with these first preliminary steps? Okay, well, next thing we can do then is let's take this entire exponent right here, 1/5. That's going to play the role of the p we see here in property number 7. And we'll bring it down as a coefficient. So we have 1/5 of log base 7 x y power 4. And I should mention right here, there's more than one ways to do this. Or you could say there's more than one ways to skin a cat when it comes to logarithms. Some people might have done this. If you distribute your exponents first, your answer is going to look different to start, but we're all going to end up at the same result. I decided to pull out the exponent rather than distribute it. So I'll be distributing it in a different way. That 1/5 is going to distribute kind of like the negative sign throughout the group. But it's really your option. You can do these in any kind of order. So for the next one, let's do the same thing with this z squared here. That's going to be a coefficient in front of the negative sign. And so this will turn into minus 2 log base 7 of z. So we use property number 7 twice to handle the power 1/5 and the power 2. We didn't do too much on that step, but I'd say when you're learning these for the first time, this is a good way to go. It's possible to do this in just one shot and write down the answer, but I would only do that if you've just practiced and practiced and practiced with this, that you can't stand these middle steps any longer. You can see the answer. If you get to that step at the end of this course, then you're on the right track. That's kind of the goal with this stuff. The only thing left to do here is take care of the fact that there's a multiplication and still a power 4 that we have to deal with. Let's deal with that multiplication first and write this in as it's now equal to a 1/5. We need to bracket because we're picking up 2 terms. Using property number 5, it's log of x plus, this is log base 7. Let me put in that base. Log base 7 of y power 4. Then minus 2 log base 7 z. So I'm dropping some color coding. I'm only putting in the color coding when we use a new property on these next steps, which I think makes it a little bit more readable for these longer problems. So last things that we have to do here, let's take a look. Really not a lot, right? We want to expand the 1/5 throughout. And also, there's still a power 4 right here we want to handle. We'll bring that down as well. So on the next steps, you could write this in as, first I'm distributing through, so 1/5 log base 7 of x. And then I'm going to put 1/5 here, but also the 4. 4 comes down as an exponent to start. Then we're multiplying 4 by 1/5. That just turns into 4/5 of log base 7 of y. So that's the process with this so far. Does that make sense to folks on the distribution and the 4 coming down? Awesome. Then this is just copying in minus 2 log base 7 z. Finally, that's the whole process to this thing. This one I think is a lot trickier. This is probably more of a worst case you might see in an ALEKS problem. Well, any questions at all, folks, on running through this one? Okay, logarithms are definitely weird. And once again, really weird about this is that one looks like the simplified form, but yet it's all very, very context sensitive. In calculus, you actually want this for certain problems, differentiation primarily, sometimes integration. But if you're solving equations, that's not the right form either. That's why we're doing all these jump through hoops with logarithmic properties. The properties you actually need just depend on the context. So let's try off one more. I think this one is actually worse than you would ever see in ALEKS, but just for the sake of practicing these properties, here's our next one to give a try. Give a try with, I think it would be the words to that. Okay, so here's our problem above. And looking at all this, good to kind of look before we leap and just analyze what we're probably going to use. There's loads of multiplications throughout the numerator, so we'll use property 5 a whole bunch. There's a division, so that should be our start on this one. But also with the 8th root, we can make that a 5/8. Use property number 7 to get through the problem. So again, very first thing you'd want to do on these is actually really just use property number 6 to start. If you see a division in this kind of format, it would be a good first property to use. So this would turn into log base 3 of 3x x squared plus 3 to power 8. But notice when I wrote that down, these things are all multiplying together. If you decide to use property number 5 right here and now and write this as log base 3 of 3 plus log base 3 of x plus log base 3 of x squared plus 3 power 8, you're on the right track. That's the goal with logarithms, to see a bunch of steps that you're supposed to do and just write them in. But we're learning this, so it's a good idea to go slowly at first. So when you're first learning this, methodical is better. I'll just do this one step of the division. It causes a minus right here. And then we'll put in the log base 3 of the denominator. Let me see if I can fix that. When we put in log base 3 of the denominator, let's also fix this 8th root that we're dealing with. We'll have a 5x plus 3 to the power of 5 divided by 8. So that's our setup so far. Now we're just going to use property number 5 to break this up and property number 7 to pull down that exponent. Any questions so far, folks? Okay, let me re-highlight here. So to start, we have 3 multiplications here, here, and the x squared plus 3. This is only specifying an xy, but that's just for brevity. This could have said log base b of x, y, z, w, and it'd be log base b of x plus the next one, and so on. So actually it doesn't matter how many factors you have here. You're still using property 5 in the usual way. It turns into log base 3 of 3 to start, plus log base 3 of x plus log base 3 of x squared plus 3 to the power of 8. And if you put your 8 right here, good call. That's where it's going to eventually go. Here, I'll do that property with the 5/8. This is property 7. It'll just come down as an exponent. So it'll be minus 5/8 of log base 3, 5x plus 3. So we're definitely on a good shape with this one. I'm also honestly thinking part E might have been easier than part D. I think what made part D hard is the 5th root affecting x and y power 4. But part E looks worse. It's actually going a little bit faster. Well, there still looks like one last thing to do. Any questions at all, folks, so far? Okay. I would say the one last thing we have to correct is that h right there. If we're expanding things as much as possible, that's interpreted as the 8 should become a coefficient for our last step. That's kind of unfortunate if I missed that here, but again, it's not a bad idea to go slowly and methodically. Our last thing is log base 3 of 3. And hang on, if I look at that really carefully, that simplifies. log base 3 of 3 should be, anyone see what the number really should be? Exactly, it ought to be a 1, and that's property number 2 right here. So that finally came up. That's nice. And that should have been a 1. I don't think that's something I would have taken off points for, but Alex might have complained your answer is not in its most simplified form. Probably that's what's going on if that message ever comes up for you. Then more copying, log base 3 of x plus, here's the one property that we're using on this line, the second property rather, 8 comes down, and we have log base 3 of x squared plus 3. Then now I'm just copying minus 5/8, log base 3 of 5x plus 3. And now I'm starting to remember, the reason part E I think of as the slightly harder problem is we also have to know where to stop on these kinds of problems. We can actually miss points on, say, a final exam if we went any further on this, because part of the concept on this is knowing when to stop. There is no property for plus or minuses. So there's nothing I can do to make this any simpler. Log base 3 doesn't distribute through it or do anything fancy. We just have to stop right at this stage. I think this deserves a comment since it's tricky enough. We cannot expand these further. Really tempting to do, but that's the same warning that we're talking about before. Logarithms can't be broken up across additions or minuses, although that one's an addition as well. The power 2 here, this one can't even move down because the only way power 2 moves down is if it's exactly in this form in property 7. Add a +1 to that and the whole thing falls apart. The property is now invalid. So this is where the problem ends. Any questions at all, folks, on solving this one? Okay, well, that's expanding logarithms as much as you possibly can. Now what we're going to do is turn all this around and look at compacting down logarithms as much as possible. Let me get rid of this first and get some space. And here's this last concept for the notes today. So this is a process that we're really going to take advantage of in the coming notes, the last 2 sections of the course. If we are dealing with logarithms and we want to solve equations, suddenly this expanded form is no good. We need to compact the logarithms as much as possible if we're trying to just solve an equation. So all we're doing in example 5 is the total opposite of part E. In example 5, this is the question, and that's the answer. So we're reverting everything. But we're still just using the same old properties of logarithms. So the real idea with example 4, even though it's for calculus courses, it's just a great way to learn these properties really well if we see it in the forward direction and the backward direction all at once. So it says here, right, as a single logarithm with a coefficient of 1. And that's not so bad. Notice there's no coefficients in front of either one of these logarithms. So we can just jump right down to property 5, compress them together, and we will get log base 4 of 5. And you don't have to put this multiplication bullet in. I'm only putting that in the notes to emphasize the addition went to a multiplication right here. Well, at this stage, there's, well, not much you can do with this. That's the answer, log base 4 of 5 times p. I guess you could take another step and just write out without the multiplication, but your answer is completely valid in this format. So that was definitely a good warm-up question. Not much to do on that one. Any questions at all, folks, on that? Okay. Well, let's see how much wilder it can get. Part B is asking us to take its log base q of 5 minus 1/2 log base q of 25 and simplify this one as much as possible. Well, first thing we have to deal with now is that negative 1/2. And like I mentioned before, you do have options. You can leave the negative right where it is, or you can move negative 1/2 and leave a plus in the middle. I think that's kind of confusing, so I'm going to leave a negative in the middle. For me personally, I think that's a little bit easier to work with. But that's a personal choice. If you do it differently, you don't have to change. So I'm going to leave that negative right where it is. Guess we don't have to highlight it yet. We're only doing one step. And this turns into log base q of 5 minus log base q. 25 was the input, and now it has a power of 1/2. But that's not a bad way to write that. But another way you could have written it was 25 power 1/2 is really the square root of 25. And this is just easier to deal with. So I'll write this in as a square root, and then we'll go on to the next step. Or we could possibly do both at once. I think this is a good time to handle the negative sign. If there's a negative, go to property 6 and think division is what you're going to get as your result. So now this is log base q of, we're down to just one logarithm, 5 in the numerator. The minus that's highlighted turns into a division bar. And this is a glorified square root 25. So it comes in this way. And now this is, if it was a real exam question, you've done most of the work at this stage. It's compacted as much as possible, but we can still simplify right here. This is log base q of 5/5, which means it's log base q of 1. And that means there's an immediate answer to this thing. Anyone see what this should come out as numerically? Good call. This must be a 0. If you ever see a 1 inside here, that's a freebie for sure. Every single time this occurs, you will always get a 0 out. And that's property number 4. So finally, property 4 came into play. Wonder how many times I can copy this screenshot before it starts to get too fuzzy. Let me know if this gets too fuzzy and it's unreadable. But looks like we've got it, folks. We had something that was expanded in its compactified form. It obviously looks like it was a 0, where here it's kind of hidden. Any questions, folks, on that one? Okay, let's compress a couple more. So same kind of stuff with this one. I'd say the only thing really new is there's just more terms more than anything. So we have terms like this 1/2 that we have to deal with before anything else. So let's take care of the 8, the 2, and the 1/2. Like before, I think it's a good idea, wise judgment, to leave the negatives right here if you're doing this as a multi-step problem. And this will then turn into the natural log of x to power 8. Then minus the natural log. This 2 right here is becoming an exponent to x minus 1. So here you could use brackets or maybe a really large parenthesis to start. Then a new parenthesis for x minus 1. And here's where the power of 2 lands. It becomes an exponent to that entire group now. Then one more. This one's a 1/2. So we're going to turn this into a square root symbol. And the square root will encapsulate all of the x plus 3 this time. So now it's minus natural log of 1/2 turning into square root symbol, and x plus 3 going inside. So that was our first step. We used property number 7 3 different times to just move all the exponents into the coefficients into the exponent positions. Does that look right to everyone so far? Awesome. Next thing I would do at this stage is, let's take a look at the sign. We have a positive here. So that's going to stay in the numerator. And everything that involves, let me get the right highlighting, everything that involves a negative sign goes down to a denominator. At this stage, it's good to compress it as all in one shot. It'll turn into the natural log, put in a big parenthesis. And again, let's put down the note that I was mentioning. Here, this is a coefficient of positive 1. So it stays in the numerator. I'll just say top for numerator, running out of space here. Anything that has a negative sign goes to the denominator. It could be done in a single step. You could take natural log 8 minus natural log x squared minus 1, use this property here, and you would have x power 8 divided by x minus 1 squared. But this is also going to the denominator as a next step. So it's probably a good idea to just run it in as here, x power 8 stays where it is. The minuses give us a divisor inside the logarithm statement. And then we just grab all the inputs. Here's x minus 1 squared to start. And from this one, it'll be root x plus 3. Finally, that's the whole expression on this one. If we were to expand this out, we would have put natural log x minus all of this. And then that negative sign could distribute, giving us these two values here. But does that look right to folks on this one here? Okay, let me take this. And before we take a look at part D, let's pause on, say, this part C right here. Another good strategy on the exam, it's a 2-hour exam, so you do have opportunity to look at some of the work you've done and just see if it's reasonable. So if we're not too sure on this one, what we could do is, let's imagine we're trying to expand it and see if we end up on this right here. So here's my really quick check. Unfortunately, the check is a whole problem in its own right, but sometimes you can see stuff you might have missed if you go in a different direction. Here we were compressing, and my check is, let's see what happens if we expand. So natural log, x power 8, x minus 1 squared, root x plus 3. If we were to expand this out, here's how it would go. First thing we handle is the division bar. I write in natural log, x power 8. Division turns into subtraction, and it'll be natural log, x minus 1 squared, root x plus 3. Then from here, 8 can come down as a coefficient. So 8 natural log x minus, here, these two things are multiplying, so we're going to get a plus. So go bracket, natural log, x minus 1 squared, plus natural log, root x plus 3. Then there's a couple more things we can do, but you really only have to do your check for as many steps until you're fully convinced you've got the right thing. For me, I'd probably do one more step. Let's call this 8 natural log x. The negative sign distributes in, so it's minus natural log x minus 1 minus natural log root. Let's actually call this x plus 3 to a power of 1/2. And that's not the full expression that I would want to expand. Oh, I forgot a power 2 on this thing. 2 can come down as a coefficient to give us that 2 right there. This 1/2 can come down as a coefficient to give us that 1/2. But at this stage, I'd be totally pretty convinced. I'd say totally convinced we really have the right stuff. So I would end my check right here. The expansion of this does give us the thing that we want. Any questions so far, folks, with either compressing it down or doing the check with expanding it? Okay. Well, looks like there's a part D, and that's our last part on this before we just do another change of base for the fun of it. So one last question, and then we'll change topics. Okay, so we have something, not too different on this one, really. Just different values. We have a z, an x, and a w, so lots of weird variables. But it starts off pretty much the same as before. Really, one thing you might notice is on these notes, I really don't have a ton of different types of problems because there's really, once you get used to all these properties, there's not a lot of variations on writing down problems. So this one, to me, already kind of feels familiar with what we've done. We want to take all of these coefficients and putting them in as exponents as our number one step. So this is going to be log That means it's log base 10, but just writing log is faster, of z to power 2. Honestly, the easiest mistake I would make on this one is penmanship. If that z looks like a number 2, then it's easy to get mixed up and put in like a 1 right there or something like that. Or put in like a 4 rather. So now next it's going to be minus log of the 1/2 will turn into a square root of just x. Then let's do it again, minus log. We're affecting w this time. The exponent is 1/2. So we can throw it in as a square root as well. Then finally, last thing we can do is, let's see, we've got a negative sign here and here. So those will cause a fraction bar, like the one right here. And everything associated with a negative sign goes into the denominator. So the problem ends by writing down log z squared on top, put in division bar, root x goes below, and so root w also goes below. And honestly, this is kind of a weird way to write our square roots. There's one additional property with square roots that we could take advantage of that says the root of a times the root of b is the square root of a times b. It's a great formula. But again, it's always worth reminding ourselves with square roots, natural logarithms, there's no formula for addition. There's lots of great stuff if it involves multiplication and division, but addition and subtraction breaks down completely. So back here, let's use that property, root x times root w. I mean, this is not a huge step, but in case Alex ever complains, this is what they're wanting. It simplifies a tiny amount by writing it as z squared over root xw. So that's the end on this problem here. Well, any questions or comments, folks? Yeah, go ahead. Or this form right here. I honestly would say if I'm grading it for the final, I'll accept either version. I would say this is the better version. It's the more simplified, but it's so small. It's more of a stylistic way of writing your answer more than something that's more correct than the other way. So I would accept this for full credit on a final. Other questions about that so far? Okay. Well, we did it, folks. That's properties of logarithms. We just have a couple more questions before we call it a day. And we'll be seeing these properties more as we go forward in the course. Really, we're going to be looking at equation solving. So we're going to see a lot of stuff like this get compacted down into a single logarithm so we can solve some kind of related equation. But first, let's make this our last problem for the day. We've looked at this change of base formula a lot. It just kind of comes up whenever we're calculating stuff. But here's where it's officially stated. If we need to take the log base b of x, this is the full change of base formula. You just take log base a of x, where a is your preferred base, divide by log base a of b. And honestly, I don't know a lot of people that use this formula in that general form. Usually, if you're using the change of base formula, it's probably going to look more like this. Instead of using log base a, if any logarithm works and you're just trying to calculate, natural log is a really good choice. It's easy to write, and there's a dedicated button for it right on your calculator. Same with log base 10, but this one's easier to write, so I usually go this route. The idea for change of base is, let me get the colors fixed. Your x will go into the numerator, so natural log x. Your base will go into the denominator, so natural log b. So that's the change of base formula in the way that we are more likely to actually use it. And here's a couple kind of relaxing problems compared to what we've just done, just using this. These are questions in ALEKS as well, so they're kind of the freebie questions. They're kind of fun. So it says, this time using a calculator, evaluate the following, and we'll round it to, I need to make a really small change here. I noticed 2 decimal places doesn't work on the second question. It looks silly. Let's go for 4. So first one to start off, we have a base of 7/11. That's really kind of strange and awkward. An input of 8. And so we can say this whole thing is no different than natural log of 8 in the numerator divide it by the natural logarithm of 7/11 in the denominator. Then from here, we pretty much have it. We just need to crank it out. So find the ln button on your calculator and let me know if you're getting anything different. So natural log 8 divided by the natural log 7/11 rounded to 2 decimal places, or we're going for 4 now, we would get negative 4.6007. We'll need to do this kind of stuff when we're solving equations, since occasionally when we solve equations, we want the exact answer. That's the exact answer. But we also want to have an approximation of it. So we use the change of base to show what our exact answer approximates to. So we'll use these ideas here whenever we're solving equations. But how's that look to folks? Are we all getting about that quantity there? Awesome, glad to hear that. Well, let's try it out one more time. It says, using a calculator, evaluate the following. Let me make this a little bit bigger. It's e to the power of negative 3 log base 2 of 4. So, well, that's kind of awkward. Really, the major thing we have to handle is log base 2 of 4. So let's write this in as e to the power of negative 3 times. Now, the input is 4 right here. So we're going to put in natural log 4 to start. Then divide that by natural log of the base, which was base 2 for that logarithm. So natural log base 2. So that's what it would look like on paper. If you're putting this into a calculator, say the TI-30X2S, this is what it would look like. It would be e to a power negative 3 times natural log 4 divide by natural log 2. And notice the 2 close parentheses right here for safety. So that's probably what it's going to look like when you go to type it into your calculator. And let me know if I'm getting anything different. Let's throw this into Desmos and see what we can get out of it. E to a power of negative 3 times, or I think I need parentheses, negative 3 times natural log 4 divide by natural log 2. And it turns into 0.0025 after rounding, 0.0025. Occasionally, we'll have to do these kinds of calculations as well. If we're dealing with, say, exponential growth, exponential decay model, this is a pretty familiar computation. But if we have a weird logarithm, change of base will save us so we can throw it into a calculator in a fast, reasonable way. Was that look right to folks, the 0.0025? Awesome, that's good to hear. Well, I think this is probably a good stopping point for us, folks. When we come back on Thursday, we'll be in the next section, section 6.6, solving equations. Then there'll be the last section, 6.7. So we're just about there. Any questions at all, folks, before we call it a night? Yeah. Oh, you're right on that one. I didn't even see that. Properties of logarithms could have just been used on that one. That would have been the better approach on this. If you can calculate exactly, let me write this in. And thanks for spotting that. I just totally just sort of read right over the fact that it could be done that way. You'll get e negative 3 to the power of, yeah, the power you need to put on 2 to get a 4 is just 2. It's e to the power of negative 6. And that's way easier to put in a calculator. E power negative 6. Same exact result. Thanks for spotting that. I think that's the better approach for sure on this one. I'll change my notes and put in something that's actually a real calculator problem for next semester. Other questions so far? Okay. Well, have a great afternoon, folks. And again, before Thursday's class, we could be in here if they're still having difficulties with the projector. I'll mass email the class again just to let you know. You'll probably see stuff on the chalkboard that will say, go to the other room if there's a problem like that as well.